Hi, gentlemen. Today we will be discussing the combined gas law as well as Boyle's, Charles, and Gay-Lussac's law. The new unit that we're focusing on is focused on gases. So we're going to take things like pressure, volume, and temperature and see how changing those things affects how a gas reacts. So we've talked about states of matter. You've seen this in previous years, but let's just review quickly. All states of matter move, whether it's vibrational, translational, but it's going to move. So you see a solid, there's still vibrational movement. Liquid, there's a little bit more. You're seeing translational as well as a lot more movement. And then finally, gas, you see movement everywhere. It's bouncing off the walls. It will fill the container, as will a liquid. Okay? As you add energy, you get more movement, which creates less density. So you would move from solid to gas. Whereas if you're moving from a gas to a solid, you're removing energy, there's less movement. No matter what, though, there will always be movement. There will always be interactions. Pressure is a measure of force per unit area. Okay, so how much force is put on different parts of an area. The atmospheric pressure, this is the force per unit area exerted by air on all objects. So this is basically in your room, how much force is put on everything by the air. Standard temperature and pressure, we'll talk about that a little bit, but this is just a way that in a lab we can set standards. So standard temperature and pressure, we're talking about 0 degrees Celsius and a pressure of 1 atmosphere or 101.32 kilopascals, and we'll talk about what those units mean in a second. Standard ambient temperature and pressure is what we usually use in the lab, right? 25 degrees Celsius and a pressure of 100 kPa or kilopascals. Okay. The units for pressure, we use pascals, and a pascal is a Newton per meter squared. Atmosphere, ATM, 1 atmosphere is about 101.325 kilopascals. Millimeters of mercury, 760 millimeters of mercury is 1 atmosphere or 101.325 kPa. And a torr is the same as a millimeter of mercury. So these are things that you need to understand. Millimeters of mercury comes from barometers, right? Mercury moved up and down based on the pressure. Atmospheres, we've tried to standardize that just like we use the metric system, because as you can see, kilopascals can be a bit of a tricky, sort of have weird numbers, right? So we use these units to help us measure pressure. Temperature, we've talked about the Kelvin scale in the past. Absolute zero is this hypothetical temperature. We haven't gotten there yet, but we believe it's the lowest possible temperature in the universe, and it's about minus 273 degrees Celsius, and at this point nothing moves. Okay, there is zero thermal energy, which means there isn't even vibrational movement. The Kelvin temperature scale starts at absolute zero and moves up. So it still works on a degree Celsius, but you're starting at a 0 Kelvin, which is minus 273, and counting up. So this saves you having to deal with negative numbers. Water is going to freeze at 273.16 Kelvin, which is 0 degrees Celsius, and boils at 100 degrees Celsius or 373.16 Kelvin. Okay, so basically you're going to take your Celsius, and you're going to add 273 to use the Kelvin temperature scale. So these laws have come from experimentation. How does gas react when you change one of these 3 variables? And you guys saw this in the lab that we did to start the unit, right? With the balloons, and you weighed the mass. If you change the number of molecules in there, the volume changes, right? When you heated the empty flask, the volume changed. The pressure stayed the same, but the volume changed as a result of the temperature. Okay, these are just some examples. I'll expand on those some more in a minute. But we can combine them all and see the relationship between pressure, volume, and temperature. We take an initial pressure, volume, and temperature. If I change one of these other variables or 2 of these other variables, how does the third one change? So this combined gas law comes from 3 other laws, from 3 experiments that we're gonna go into a little bit more detail, but I'm going to introduce them to you first. So Boyle's law was the original one, and it it deals with a constant temperature. So temperature kind of cancels out of this combined gas law, and you're left with P1 V1 equals P2 V2. And that works just like we did with the dilutions in the solution unit. So C1 V1 equals C2 V2. Instead, you're using pressure and volume. So if you change one pressure, if you change the pressure, the volume will also change as a result with constant temperature, or vice versa. Just think, if you make the vessel smaller, just think of the syringe activity. As you pushed down and made the volume smaller in the syringe, the pressure increased as a result. Okay? If you make the volume bigger, the pressure goes down. There's less push. There's more room for those molecules to move. Charles' law, this is now if you have that constant pressure, right? So this now, we're looking at the balloon with the flask. Okay, you take the balloon from the flask from the cold water to the hot water, the molecules start moving faster, and the pressure has to stay the same, but the balloon changes the volume as a result. Okay, so that you increase that temperature, the molecules are moving faster, and the volume increases. And last but not least is Gay-Lussac. Okay, in this case, you're dealing with a constant volume. And so now you saw this when you had the stopper and you had the flask. You put the flask from cold water to hot water. The volume stays the same, the temperature increases, so the molecules move faster, they push harder, increasing the pressure. As you cool them down, the temperature decreases, molecules move less, you have a lower pressure. Okay, so let's just take a look at one of these experiments. We'll use combined gas law to start. Apologies. Okay, so this is the type of question you might see, and we'll start next class with a few of these practice problems, and then we'll go into talking about Boyle's, Charles, and Gay-Lussac's law. Okay, so in this case, you can recognize that you're given a volume, the pressure, and the temperature. So you have a gas that occupies a volume of 20 liters at a pressure of 5 atmospheres and a temperature of 500 K. So I can say my volume, my V1, is 20 liters, my P1 is 5 atmospheres, and my T1 is 500 Kelvin. Okay, I can also see that the question asks, what will the volume be if both the pressure is raised to 10 atmospheres and the temperature is changed to 250 Kelvin? So I'm given my P2 of 10 atmospheres, and I'm given my T2 of 250 Kelvin. The question now is, what is my new volume? So now you're just plugging these in and rearranging your equation. The equation is P1 V1 over T1 equals P2 V2 over T2. So here now you have your combined gas law. And we want to isolate for V2 and solve for that. So let's start by moving T2 over. Multiply both sides by T2. End up with P1 V1 T2 over T1 equals P2 V2. Okay, and now I'm going to need to isolate my P2, so I'm going to, those cancel that. I'm going to isolate this, so now P2 comes over to this side, these two cancel, and now I'm left with my V2 equals P1 V1 T2 for T1 P2. Okay. Now all you're going to do is you're going to take these values, plug them in, and solve. So I'm going to let you do that. That'll be your last task on this example. Now, just before I do that though, you can see now where Boyle's law or Charles' law comes in to play. If I were at a constant pressure and the original pressure was the same, these would cancel out. Right? If I had this temperature was staying the same, the temperature would cancel out. So you can see now where these other formulas get derived from. So try this, answer the final question on Edpuzzle, and then we'll do some more practice problems and talk about Boyle's, Charles, and Gay-Lussac's law in class. Thanks, gentlemen. Good luck.